Hello everyone and welcome to the last exercise sheet for renewable energies. Today we want to talk about the Betz limit and some other interesting stuff about wind turbines. So I would say let's start and dive right in. And we are starting with the first task here, where we want to compute the blade geometry according to Betz. So our task is that we want to calculate the chord length, T of R, as a function of the radius. Using the inflow angle, I misprinted here as the angle of attack, but I really meant the inflow angle, because they're not the same actually, and also using the lift coefficient. I hope this doesn't confuse you as much, because the angle of attack and alpha that we will use here are slightly different quantities, but I hope you noticed that. Okay, so let's start right now. First, maybe explain what we want to do. So we consider that we have a classical wind turbine, which looks like this. So here we have our blades. They are some sort of shape like this. It's not very beautiful, but still, I hope I make my point clear here. So in the script you can find some better drawings for that. Okay, so this has a certain shape. So this shape here we want to calculate, or the thickness of that. This is our chord length. And we want to know how does this look like. This is called the blade geometry according to Betz. Oh, sorry, I made a mistake here. So I want to draw here a circle. And we are now, and we will come back to this drawing a little bit later. So task number 24. So we start with the power of the wind, and we assume that our turbine is working in the Betz limit, so it can extract the maximum power. So first, let's write down the power of the wind. So we already know the power of the wind. In the rotor plane. That is something that we used several times already, and simply our power is nothing else than the time derivative of the energy. So it's something like that, m dot over 2 times the velocity of the wind far in front of our wind turbine, because the velocity is not changing here. That's our assumption. Only the mass of air that is flowing through the turbine may change. So this is our power, and using dm is equal to rho times the volume, we can write this as the time derivative of m is equal to rho times the area and the distance in the wind direction, which as a derivative with respect to time. So we can see using this is just the velocity v1. We can substitute this into this formula, and therefore we get 1/2 times rho, or maybe it's better to say that this is the whole area here that we are using, the whole area, which is denoted here. Okay, so this is just 1/2 times rho times the area times the velocity cubed now, because we have an extra term of velocity coming from here. So just another derivation that was already made in the lecture. And now we are assuming the Betz limit, so the power that we can extract, or maybe we call it Betz power. This is just the Betz coefficient times the power that our wind has. So 1/2 rho times a v1 cubed. And as we saw in the lecture, this is a very peculiar number. It's namely 16/27, something like 0.59. And this is the power that can be extracted from the wind here. 16/27 rho over 2 v1 cubed. And now we rewrite this area here as pi r squared, where r is just the length of the rotor blades. Okay, pi r squared. And now we are looking for an infinitesimal contribution of the power. And here we just assume that we take a small ring. Hopefully I can draw this. Okay, it looks fine. We take here a small ring with, I don't know, maybe let's switch back to the pen again, with thickness dr. And then our power, our infinitesimal power, just looks like this. 16/27 rho over 2 v1 cubed. And now we just have to differentiate this here, which becomes then 2 pi r dr. So just using this small ring and not the whole power. Obviously, integrating over that will give us the total power back, of course. So this is just 2 times pi r dr. Okay. So what do we also know? We know the relation between the force and the power by using the velocity. So we can write the power just as force times velocity. And now we have to note, that was already argued in the lecture, that we only need the parallel components for our contributions. So only the part parallel to the rotor blades really contributes to the power that can be extracted. So let's write this down first. So only the part parallel to the rotor blades contributes. Okay, and this means that our power that we are looking at is just the parallel part df times the velocity, so the velocity of the rotor blades, or of the wind in there. No, actually it's the velocity of the rotor blades. So and this is just, as we know, for certain distance r from the center, this is just omega times r, assuming that our rotor blades are rotating with a velocity, angular velocity of omega. And now we generalize this for n blades. So if we're not using one blade, the power contribution becomes just, so for n blades, we have a multiplicative factor with n. So the power that can be extracted by the wind turbine is n times the parallel force times the velocity of the wind blades at certain distance r. Okay, so further we now want to assume that the only contribution to our energy is the lift. So we want to neglect all drag impacts because they will probably be very low. So for the classical wind turbine that we have here, the most contributing factor is actually the lift and not the drag. Whereas for other wind engines, and we will come to that in one of the next exercises, some other wind engines use actually drag. But here we assume lift. So we assume, let's write this down. We assume that the only contribution to the I can't say it. Azimuthal force. OMG, that's really bad. Is lift. Okay, so we neglect drag. Drag is neglected. So now we want to see how the force looks like, sort of. So maybe let's do a little derivation to motivate this formula. You can also find this in the script. So for the force due to just lift, we can here write rho over 2 times the velocity in the plane squared times the effective area that the wind sees. And also, no, actually A is the effective area, yes. And we can rewrite this using a new velocity term, and we call this C, and the C is just the inflow velocity. And we multiply this by the chord length times sort of some sort of length of our rotor blade, so to say. And this is the actual area of our blade, but we write this effective term. So the effective area, we rewrite this into our velocity. So instead of the real velocity, we write an inflow velocity, sort of to make sure that the effective area is does only contribute here. Okay, so I hope this is a little bit understandable. So let's write this infinitesimally. And we can see here that just by replacing B with dr, that this looks like this here. So rho over 2 is the same, c squared times t times dr. And this t here, so maybe we should mark this, highlight this a little bit. This t is the chord length, and this is the quantity that we want to find. So t is the chord length. Okay, so this looks fine, I guess. And now let's make a little drawing to see how the parallel component of this force looks like. So maybe I give first the formula here, and then I try to derive it. So the parallel part is just the total lift part. So maybe we should give this also an index A for German Auftrieb. And here we mean the lift times the sine of this angle of inflow, alpha. Okay, so this is not the angle of attack, it's the angle of inflow. And for that, maybe let's do a little drawing here on the next page. So suppose that we have here our blade, which looks a little bit like this. And we have our rotor axis looking in this direction. So this here is the rotor axis. Okay, and here we have our velocity of the blades, omega times r, and our new quantity is c. So this is c, the vector of inflow, yes, okay. And this is our velocity of the wind in the plane. Okay, so this is a drawing that you also made in a lecture. You can look this up. And we define that the angle of inflow alpha, this is just the angle between our velocity of the rotating plates and the inflow velocity c. Okay, so now we can find that the force can be written as a part which is drag and another part which is lift. So this is lift and this is drag. I think it has an index of W. Okay. And now we want the component that's parallel to the rotor axis. That is our interesting component here. And we find this parallel component just by looking here at the projection onto the rotor axis. And noticing that the rotor axis is perpendicular to the rotation direction omega times r, we see that here we have a right angle. And also between the inflow velocity c and Fa, there's also a right angle. So we will find the inflow angle here again. And here, from this figure, we can see that our parallel force is indeed just the sine of alpha times Fa. So let's write this down here. Maybe dF parallel is this. And the red one was the lift, the total lift. Okay, so. And we also want to note that for an inflow angle of 0 degrees, so if our inflow is some sort of parallel, so coming in front of our rotor blade, then we don't have any lift here. Okay, so now what we can do now, we can substitute this into our formula for the power. So let's write again the power here. This was just for n rotor blades, d times F parallel times omega times r. So this is the same that we wrote here. So, and now substitute, substitute now the force into this formula. And then we can see that it looks like this. So n times omega times r, this is what we already have, times the rho over 2, c squared. Now the chord length t of r, dr, and maybe I missed something here. Also the, I missed the lift coefficient actually. So here is also the lift coefficient, which I somehow forgot to write. So we also have the lift coefficient here, Ca times the sine of alpha. So, okay, now we have an expression for dp and also for the Betz power. So this dp Betz here can now be compared to this power here, to the extracted power. And now we only demand that they are both the same. We demand dp is equal to, or must be equal to, dp Betz. And what we find is the following relation. Just substituting the results, we see that we have 16 over 27 times rho over 2, v1 cubed, 2 pi r dr. It must be equal to the expression that we wrote here before. Let's write this again. N times omega times r, rho over 2. Now the chord length, the quantity that we want to find, Ca and sine of alpha. Okay, so what we have here now, we have some same quantities on the right and the left. So this dr cancels out, this rho over 2 does cancel out also. And just rearranging this equation a little bit, we can find the chord length. So T of R is just bring the n to the other side, 1 over n. Then we write the 16 over 27 again. And now a huge fraction here. So we have this 2 pi r on the left side and the velocity also. And in the denominator, omega times r, c squared, the lift coefficient times the sine of alpha. Okay, so this is already a valid expression here, but you had to find the solution just as a function of radius, angle of attack, so not angle, the inflow angle, sorry, and the lift coefficient. So we have to substitute the velocity here. Okay, let's do this using another wind triangle. So basically we are just redrawing the one that we already wrote here. Just in a little bit simpler way. So this is here our, or maybe I need a bit more space. Okay, so, and we again have this omega times r and the inflow, so the velocity v2 and the inflow velocity c. And of course the inflow angle alpha. And from this wind triangle, so using the wind triangle, we can find some useful relations. Namely, we can find that V2 is connected by C times the sine of alpha. Just using that the sine is defined as this length over the hypotenuse. Okay, and also we can find that omega times r, so the other length, is just C times the cosine of alpha. Okay, and now we can use the Betz limit again. So for the Betz limit, we derived that the velocities far in front, far behind, and in the plane of rotation are connected to each other. And here we know that the velocity v2 is just 2/3 of the velocity v1. So maybe you're more familiar with the formula that v3 is 1/3 of V1. And from this relation, and using the Froud-Rankine theorem, which states that V2 is just the arithmetic mean of the other two velocities, we can find this relation for V2 and V1. So we can find, using this relation for V2 and this for V2 and V1, that V1 can be expressed as 3 over 2 times c times the sine of alpha. Okay, and now we can substitute this back into our expression for the chord length. So this, maybe we call this equation star. We can substitute this back into star and find that T of R is just 1 over n. This stays the same. Also the 16 over 27. Now we have again the fraction here. And we have this 2 pi r again. And now 3 over 2 c times sine of alpha cubed over. And now we also resubstitute this omega times r with c times cosine of alpha. So c times cosine of alpha times c squared times the lift coefficient Ca, a lot of c's in here, times sine alpha. Okay, so we have some quantities that cancel out. Let's find them. First of all, we have the c here, c cubed in the numerator and c cubed in the denominator. And also we have here sine of alpha cubed, and this cancels with the sine in the denominator as well. And also here we have 27, which cancels with the 27 down here. Okay. So, and also we have an 8 here, and this 8 cancels with this 16, leaving us a 2. So in the end we find that this is just 1 over n times 4 pi r over Ca, and the signs, we have one sine in the numerator cancelled out, so sine squared over cosine alpha. And now this is our final result. So we found the chord length as a function of the radius, the inflow angle, and the lift coefficient, and also the number of blades. Okay, so this was our first task. I have to admit it was rather lengthy, but I think you may learn a lot solving this task. So let's add another page and move on to exercise number 25. So number 25, what do we have here? So we want to calculate the distance, the minimum distance between wind turbines. So we consider two neighboring wind turbines, and they should not interact with each other. So maybe let's do a little sketch here explaining this exercise for some of you who might not have understood it yet. So suppose we have here our two wind turbines. They are looking something like this. This is not a Mercedes star, this is a wind turbine. And yeah, they are looking like this, and they are distanced. Their distance is r, small r. And what we do behind the wind turbine, there's a wind channel created, which is larger than the original wind channel here. So it looks something like this. I hope it's understandable. And what we demand now that the wind behind the turbine does not overlap. So that these two circles here, so this circle and the other one, that they won't overlap. Okay, so let's call the areas here A3 and the area here A2. Okay, and we assume that both wind turbines are identical. Yes, okay. So let's start on that. So we also assume a maximum power extraction. Yes. So we have maybe a distance between wind turbines was the title. Okay, so, and we assume maximum power extraction, which implies the Betz limit. Yes, so the Betz limit okay, so says that the velocity v3 is 1/3 of the velocity v1. This is some relation that we already used in exercise number 24. And here again, using the Froude-Rankine theorem, I will write this down again. It's just the arithmetic mean of v1 and v3. So this is 2 times v3 or 2/3 of v1. Okay. So also we know that the airflow behind the wind turbine becomes larger, as I already indicated in the drawing. And what we can use here is the continuity equation. So or some sort of continuity between those areas. So we impose continuity as was done in the lecture also. So rho times v1 times a1 is equal to rho times v2 a2 is equal to rho times v3 a3. Okay, so the important part are the last two. This is the last equality here. So from that, using that the density of air is a constant, we can find that v2 times a2 must be equal to v3 times a3. And using the relation that we found here that connects v3 and v2, we can easily see that substituting back that 2 times a2 must be a3. Okay. So now we have a relation between the original size of the wind turbines and the size of the wind channel far behind our wind turbine. Okay. So now let's assume that our rotors have a radius r. Rotor radius r. So A2 can be computed by pi times r squared. And therefore, A3 is just 2 pi times r squared. And we can rewrite this as pi times 2r squared. And we see that our new radius of the areas far behind the wind turbine is just this quantity here, which we call r tilde squared. Okay, so we know that the width of the wind channel or the radius of the wind channel is r tilde. And we can find r tilde just as the square root of 2 times r. Okay. And now we assume that using the distance of the wind turbines, that the areas far behind do not overlap. So we say, so maybe just make a quick note here, minimum distance that the wind does not overlap. Doesn't, oh god, typo. Doesn't overlap. And this minimum distance we call small r, as indicated already in the figure. So we can find that r is simply given by 2 times r tilde. So assume that here we have r tilde. We can easily see that the minimum distance must be 2 times r tilde. So just using the formula that we found for r tilde, we can see that this is 2 times the square root of 2 times r. No, that's the original r. Yes, okay. And this is simply just square root of 8 times r, and the numerical value is about 2.8. So we can conclude that the distance between wind turbines must be roughly 3 times the radius of our rotor blades. And was there another question? Why does this assumption make sense? Okay, and the reason for that is that we don't create additional turbulences. So suppose that we want to build another wind engine a little bit behind our 2 original ones. So we don't want to create much turbulence in the air, which will reduce the efficiency of the next wind engine. Okay, so the distance is useful. Distance across the wind direction. So perpendicular, a distance across the wind direction. It's useful so that turbulence is not amplified. So battery is low, it says. I hope this survives. On the top right corner, the tablet says 10%, but I'm already charging it, so hopefully it won't power off. But these tablets are a little bit dangerous sometimes, so I hope this won't happen here. And so the turbulence is not amplified. Okay. So, okay. And indeed, one uses this distance. Actually, they are really used for distances between wind turbines. So usual distances are indeed about 3r. This is something I found in the literature. You can find it in some large book from how it's written in German. It's called Windkraftanlagen, for anyone who is interested in looking this up. Okay, and also what I found there, some other interesting fact, that the distance of turbines in wind direction. So if we have a wind turbine and the wind is coming from that direction, so we want to build another one behind this, distance in wind direction direction. This is about 5 to 6 R. So double the distance. Okay, so some interesting additional fact here. Okay, so now let's move on maybe to exercise number 26. And what do we have here? We want to calculate the thrust acting in axial direction on our wind turbine, which again runs at the Betz limit at maximum efficiency. And we want to compare this to the drag of a solid disk. So this sounds rather difficult, but actually this can be solved pretty fast. So let's do this. Exercise number 26, thrust. Okay, so let's start with this. Maybe let's scroll a little bit down here. Okay, first we note that the thrust in axial direction is given by just the Newton's second law. So Newton's second law states that the force is just the time derivative of the momentum, and the only time-changing parameter is the mass times the velocity difference far before and far behind our wind turbine, which is just V1 minus V3. And we can rewrite this again as rho times A times V2. Okay, so yeah, let's rewrite this again here behind. Rho times A times V2 times V1 minus V3. Okay. And now again, assuming maximum efficiency. We find the Betz limit, and for the Betz limit, the velocities are related using the Frood-Rankine theorem, 1/2 times V1 plus V3. So this is Frood-Rankine. You might see that this is quite important, this relation. You should remember this, probably for the exam. And V3 is 1/3 of V1, and V2 is 2/3 of V1. Okay. Now we can plug all of these components into our formula for the force, so which corresponds to the thrust. And there we find that the force is just rho times A times 2/3 of V1. This was just this V2. And times V1 minus 1/3 of V1. And this was just V3. So just using this formula here, plugging in, we find this relation. Okay. So let's rewrite this as rho times A times 2/3 V1 squared. 1 minus 1/3. And this is just 2/3. And we see that we can easily see now that this is just, maybe let's rewrite this in a little nicer form. So we have here 2/3 times 2/3, which corresponds to 8/9. Or did I make a mistake here? Yes, I think so. Where did I do the mistake? Oh, of course. I forgot the over 2 here. Of course. So So we find in the end that this is just 8/9 times 1/2 rho times v1 squared times a. And we will see in a minute why we write it in this way. So basically, this here is just the drag coefficient for some force acting on an area. And this is actually the result that we have for the thrust acting on our wind turbine. And we can compare this to the solid disk, or now let's calculate this for a solid disk. And here we use the air resistance. So this basically is just drag. And for this, we had a formula in the lecture that the force acting here is just the CV value times 1/2 rho v1 squared times a. And we can see that those formulas look pretty similar. And therefore it's reasonable to interpret this prefactor as the drag coefficient. And for a solid disk, we had in a lecture some values. And for a solid disk, we have a CV value of about 1.1. So for a solid disk, we know that CV is about 1.11. Okay, so comparing this to our wind turbine, we see that those values are pretty similar. So therefore also the thrust load is similar to the air drag of a solid disk. And comparing this, so just dividing the thrust on our wind turbine with the thrust on the solid disk, we find that this is about 8/9 times 1 over the drag coefficient, which is about 0.8. So the thrust on the wind turbine is a little bit smaller, but it's in the same order of magnitude. So we see if we are throwing such a big disk with a radius of length of a rotor blade, the air resistance is comparable to the drag or the thrust that the wind turbines feels when we have some velocity v1 of our wind. So that's actually pretty interesting, I would say. And this was all we want to calculate here for this task. Maybe the 3.5 points for this task are a little overestimate. It's, in my personal opinion, easier than task number 25. But nevertheless, let's move on to the last task, number 27, which was mainly just discussing things. Okay, so task number 27, let's start a fresh new page. Task number 27, and we are on page 28 on this document here. Pretty interesting. So this is called the glide number. Okay, and let's a little bit talk about the glide number first. So the glide number is the ratio between the lift and the drag. Okay? It's simple as that. So glide number, let's write this down as ratio between lift, which we call Fa, and drag, which we call Fw. Okay, so, and we give it a nice name. We call this epsilon, and we say that drag divided by, so lift divided by drag is the glide number, which is, as we saw here, the stuff behind this coefficient is the same. So this is just the ratio of the lift coefficient and the drag coefficient. So this is the glide number. And now we want to discuss why airfoils, so modern airfoils in the modern wind turbines have a high glide numbers, sorry. And the simple reason is just that looking at drag as energy conversion from wind speed to electricity and lift, we find that lift is far more effective for generating electricity. And therefore we design the wind turbines in such a way that the lift coefficient of this airfoil is maximized, whereas the drag coefficient is minimized. So this is the simple reason why those turbines are designed that they have a high glide number. So we are aiming for wind turbines with high glide numbers because they can extract more of the power of the wind. So let's write this down. Wind turbines mainly use lift to extract power from the wind. Drag does not contribute to the blade rotation very much. So drag is not pretty useful to generate this rotation. So drag does not contribute to the blade rotation very much. Okay, so we can see this by just going back up here where we draw a wind triangle, and here we see for the simple case that the parallel component of the drag is smaller than the of our lift. And for modern airfoils, this ratio is even higher here. So lift is far more effective. Okay, so let's make a conclusion here. Thus we should, as I already explained, maximize lift and also minimize drag, because drag also causes a lot of stress onto our engine. So both factors contribute to a high glide number epsilon. Okay, so compare this to modern airfoils, and for modern airfoils or rotor blades, modern airfoils, they have glide numbers of about 200. So the lift coefficient is 200 times larger than the drag coefficient. And maybe bring forward another interesting argument. So if we are using a wind turbine that is not using lift, So this is actually called a resistance rotor. So for a resistance rotor, the maximum drag coefficient, so CW max, that we can find is about 0.2. So we can only extract about 20% of the power stored in the wind. And this is far less than the Betz limit. So we cannot get near the Betz limit for using just drag as an energy source or as a source to generate, convert the power into electricity. Okay, and for a lift using rotor, so a classical airfoil lift using rotor, we see that the lift coefficient, the maximum lift coefficient, is about 0.5 for modern airfoils. And this is in the order of the Betz limit, which is 0.59. So we are getting close. Okay, so, and the last point that we want to discuss here is the tip speed ratio, and why a low tip speed ratio for small windmills is working well, and why we don't need high glide numbers for such wind turbines. So okay, let's first look at the tip speed ratio. Tip speed ratio. This is called lambda, and this is defined as the velocity of the blade tip divided by the wind speed. Okay, so something like omega times r divided by v1. Okay, and for example, classical wind turbines like a Western mill or so, they are slow running wind turbines. And therefore, because they are slow running, their tip speed is not very high, and therefore the tip speed ratio is very low. So for example, Western mills which are slow running turbines, they have a low lambda, have low tip speed ratio. And here, I don't want to do the calculation, but for engines of a higher fill factor, so naturally they are using drag, and because they don't get much lift using just small tip speed ratios. And what we see for low tip speed ratios, here the drag for these lower velocities, the drag is more useful. This is just due to the lower speed of our tips. It's more useful for power extraction. So no, we don't have need for high glide numbers. Oh my god, this looks terrible. No need for high glide numbers. And also, maybe to mention this point again, we have a high fill factor, or a high filling ratio. Because in order to use this drag of the wind, we need to have something that can use this drag of the wind. high filling factor for these wind turbines. Okay, so yeah, it's a rather short task here. I hope I explained it well enough. I gave some heuristic arguments, did not any calculation why this is really more useful, but the take-home message here is wind turbines mainly use lift to generate their power. This is the most important point that you should drag from this exercise here. Okay, so with this we are on the end for all of these tasks. So together we discussed 27 exercises, and I hope I did it rather well. If not, tell me, just writing an email or so. And I hope you will be well prepared for the exam. We will see us there. And yeah, with not anything to say, I hope you stay healthy and we will see each other again, hopefully. So, see you. Bye.